In the first two sections of this chapter, we talked about the results of having a parallel postulate, and that led immediately to the Kea theorem, the converse of alternate interior angles theorem. And those results were important, but now we're going to move on to area and similarity. And so we're somewhat aided by the fact that, well, we're greatly aided by the fact that in the SMSG axioms, we just have a straight up area axiom. It says the area of a rectangle is the product of the length of the base and the length of its altitude. So this is perfect. This allows us to define area for triangles and area for parallelograms, area for trapezoids. They can all be reformulated into areas of rectangles. So this is going to lead to the natural development of those area formulas. And also we're going to talk about similarity. Similarity is more difficult to deal with. The proportionality is hard to establish. So I'm actually proving, or already have done a theorem, the Basic Proportionality Theorem. So we need a few definitions. For example, parallel segments, just making it clear that if we say two segments are parallel, we're saying that they're included in lines that are parallel. And this is the most important one, the distance from a point to a line. So if I have a point P and I have some line, then the distance is defined to be whatever the distance is when I drop a perpendicular. So then if I drop a perpendicular to the line, it'll intersect it at some point Q, and then whatever the distance between P and Q is will be the distance between a point and a line. That also gives us a way to find the distance between a line and a line, right? So if there was some line up here, I can just pick a point on it, call that P, and then find the distance between P and the other line. I'm sorry, a distance between two parallel lines, right? If the lines intersect, then there's no way to define a distance between them because sometimes it's 0 and sometimes it's any other positive number. But if two lines are parallel, we can say the distance between them, we can define it based on the distance from a point to a line. And the final definitions are ones you should probably be familiar with already. A kite, which has adjacent sides, two pairs of adjacent sides congruent. Rhombus, all of its sides are congruent. Square, hopefully you know that one, but notice our definition is a parallelogram with a right angle. Now, of course, it has 4 right angles, but the definition just says that, hey, any parallelogram that has a right angle. Wait, I'm sorry, that's that's wrong. This is a rectangle. So I'll have to change that in the notes. I'll get that done here in a minute. So sorry about that. A square is a rectangle that's also a rhombus, right? All right, sorry about that. And then we get into similarity. So similar polygons are provided given two things. We need their corresponding sides to be in proportion and the corresponding angles to be congruent. All right, so in similarity proofs, we have real numbers and in these proportions, and area is going to be the leverage. Area proofs is going to be the leverage that we get on this. So let me just show you a couple of these theorems. One very important one here is the parallelogram recomposition theorem. What do I mean by that? Well, we had a parallelogram decomposition theorem, and we said that if we have a parallelogram, right, and we draw either of its diagonals, then that leads to two congruent triangles. And either diagonal will do this. Well, what is the recomposition theorem? And I'll make it clear that the idea of a parallelogram decomposition theorem and recomposition theorem, these are my names, right? Nobody else uses this that I know of, but it's how I like to think of it because it helps, it shows you all the key properties of a parallelogram. And these parallelograms, which by the way, remember, includes rectangles and squares and rhombuses. So a lot of these figures, they have these properties about the triangles formed across their diagonals. And the recomposition theorem says, hey, start with any triangle. So here we're starting with this green triangle. And if I create a copy of the triangle, you see that there in red. And then I take that copy of the triangle and I rotate it 100 degrees and then line up the congruent sides over there, I will get a parallelogram. So it's not a hard theorem to prove, but I gave you a dynamic illustration there so you can see what we're doing. Anytime I have a triangle, I take a copy of itself, rotate it 180 degrees, slide it into position, and I have a parallelogram. So we have a couple of area proofs about the first one in this section is about a parallelogram and now the trapezoid. And then there's an area proof of the Pythagorean Theorem, which I have a video of, but you can see the illustration right here. And the easiest way to do this is to take a right triangle and make 4 copies of itself. And set them up in a particular order so that we have a way to deal with everything that's there. This isn't going to be a great picture, but that's the idea. You get a big square, that's a plus b. And its side length is a plus b, so you take a plus b squared. This big thing in the middle is c squared, and you can get all of the areas that you need to prove this. There's a little bit of algebra there at the end. And then finally, the most important theorem in the section, I mean, I suppose the Pythagorean theorem is probably the most important in this section, but it's not that hard to prove. So kind of the key result that's a little bit difficult is the basic proportionality theorem. So what this is saying is that anytime I draw a line that's parallel to one side of the triangle and intersects the other 2 sides, that it will divide the sides into lengths that are proportional. So AD divided by DB is going to be the same real number as I get when I take AE and divide by EC. So AD divided by DB is equal to AE divided by EC. So that's a theorem that I prove. It's one of the two, it's 2 videos after this one in the playlist. And we use areas to prove it. So just to give you a quick idea, right, we take this area of this triangle, which crazy enough, no matter how this triangle is formed, has the same area as the triangle that I'm drawing on the right side. So those 2 are equal. This triangle is equal to itself, and we do some wizardry with altitudes and creating the area formulas for these triangles, and then we can set up equations and divide through by areas and get the proportion that we need. So you should definitely take a look at that video and understand that. The reason is because every single triangle similarity condition requires that basic proportionality theorem. And so, by the way, AA triangle similarity, you'll see some books call it AAA, and it's true that if all 3 angles of one triangle, all 3 interior angles of one triangle are congruent to the corresponding angles of another triangle, then they're similar, but I only need 2. Because we are in Euclidean geometry, and then whatever these 2 angles are, the third one is just 180 degrees minus the sum of the first 2. So I call it the angle-angle triangle similarity. And I said that you'll need the basic proportionality theorem for all of these. You definitely, if you're the person who gets to prove, AA triangle similarity, definitely look at the proportionality theorem. There's a reason that this is theorem 7 and the proportionality theorem is theorem 6. Now, there are ways to prove SAS and SSS and leverage the AA triangle similarity rather than going all the way back to the proportionality theorem. But definitely the proportionality theorem is a fundamental idea that helps push all three of these important theorems through. And then we've established all of the similarity conditions. So again, the important things here, we have our first proof of the Pythagorean theorem. There is a similarity proof that we're going to do in the next section, which requires a couple of facts about right triangles to prove it. So good luck. Definitely check out the video proofs for this section, and I'll see you in section 3.4.